So in this last video about infectious diseases in livestock, I'm going to go through a bunch of models about foot and mouth disease and avian influenza in particular. So what I want to do is give you and about space in this context. And what I want to give you is a sense of a variety of models that have been published on the subject as about the spread itself, but also about control of these diseases. And so this will be in and out of control aspects. You will see some models are purely about spatial temporal spread. Other models incorporate control. Other models really look at control as their only point. Um, I'll start without any further delay. I'll talk about foot and mouth disease models first, and we'll go through 6 different models, although the first topic I'm going to look at is many different models. So to start with, I need to get control over my slides. That's it. To start with, I want to look at models of Woolhouse. So this is someone that has done a lot of work on foot and mouth disease, starting in the late 90s and extending forward. And so I'm going to detail some of those models a little bit. Again, this is not to so much dive into the exact details of the models, but to provide an overview. Because if we had to look at the details, we would be here for hours. My first remark is that most of the models of Woolhouse that I'm going to talk about are models that, if you refer back to the lectures about metapopulations, these are models that are à la Levin's, where space is implicit. Okay. And I've already mentioned that in the preparatory lectures about foot and mouth disease. What you observe with foot and mouth disease is a lot of authors have counted infected herds, not infected animals within herds, but they just look at the presence of cases in a herd. And although this is a lecture about space aspects in these diseases, I'll point out that in the early models of Woolhouse, for example, space is entirely implicit. Space is present only insofar as herds are spatially located. And because of this spatial localization, well, you have space. But apart from that, there's no explicit mention of space. Sometimes, okay, we'll see some models of Woolhouse where there is space. So the first model I'll point out is a model from 97. So this is prior to a big epidemic of foot and mouth disease that took place in the UK in 2001. And this is a paper of Hayden, Woolhouse, and Kitchen. So the model looks something like this. So it is a model. First of all, notice I have a delta ST, delta LT, delta IT, and delta RT. That delta, as shown here, is the difference in the state between time t plus 1 and time t. So this is a discrete time model. Okay. And now what you can see when you look at it, so the variation of S of t is simply minus beta S of t I of t. So this is the classic infection, mass action infection term. For L, you have this, but you also see this term here. you can see that L increases by this quantity on essentially, if you want, the same day. Okay, so this is delta x of t. This is what happens, the change. So this means at time t plus 1. Okay, when you see this, this is the difference between time t plus 1 and time t. So the change is positive here, but it's negative here. And this is a delay term, essentially. Well, if you had a continuous time system, that would be a delay differential equation. This is a delay difference equation. And what's happening is sigma, this is the fixed latent period. So what that means is that individuals leave the latent compartment after sigma time units, which are typically a number of days. Okay? And when they do so, they enter the infected compartment. And likewise, they leave the infected compartment after new time units to move onto the recovered, removed compartment. It's in the case of foot and mouth disease, R will typically be removed because this corresponds to culling of the herds. Okay, so remember that these are infected herds. So the reason why they are moving these quantities around and not the quantity in L of t is because remember that the object here is infected herds or infected farms, not the number of infected animals. So you're not multiplying the number of latent farms and so on. The ones that became infected some time ago change status throughout, but their numbers are not changing. So that's why there's this sort of conservation here. Okay, so this is the model that they looked at the time. Uh, when the number of herds or the number of farms is large enough, they can compute an R0, which is a very classic R0, essentially from the Kermack and McKendrick type model, for example. Beta over typically that would be gamma in other models, but here this is nu, the average infectious period, multiplied by the number of individuals, in this case, the number of farms. Um, so they can use this. And what they do is that they actually obtain estimates of beta of t. So here you see this is beta at the start of the epidemic, but here this is beta as a function of time, and they obtain it by this knowledge of how many farms became infected and so on. Okay. So what they did is there was an epidemic of foot and mouth disease in 67 and 68 in the UK, and this is the data they use. Um, and so they have a time unit of 1 day. They take sigma equals 5 days. This is the latent period until detection. Okay. Nu equals 4 days. This is the average time until the farms are removed. That means how much time uh, health authority, animal health authorities take to take culling measures. And N was 16,000 hertz. Um, and as I've already said, space here is purely implicit. Uh, the only reason why you can think of space is that these herds, we knew where they were, and as a consequence, it is possible to see how things spread through space. Um, this is a later paper of Woolhouse from 2004. This is in a book, and I'll just mention some aspects that he mentions here. This is a review paper. It's really interesting if you're interested in the modeling of foot and mouth disease. Well, there's a lot of things here. This here, I'll just point out, this is the data actually from 19, uh, 1967, 1968. This is the number of infected herds. The number of infected herds is this curve. Cumulative number of herds is this curve here. Uh, and R of t is the number of removed herds. Um, sorry, so this is the cumulative number of herds removed, and this is the number of infective herds at time t. Okay, and that is considered, for example, using the model before. So one thing that Woolhouse notes, and that is quite important throughout, and so I thought I would spend a minute talking about this here, is that there is always a difference between what you put in a mathematical model and what you actually observe. And so this figure here shows the difference of what is in a compartment in theory, and that's the top, and in practice, and that's the bottom. So it's essentially, when you think about how a disease spreads from a mathematical modeling point of view, you're looking at that top part. So you say, well, animals are susceptible, latent, infectious, and removed, or farms are susceptible, latent, infectious, and removed, whichever your unit of analysis is. But at the bottom, what you see here is what happens in practice. In practice, um, you know that there's infection, then latency goes towards infectivity. But in terms of the moment you observe events, there's the infection event that you don't observe, and then at some point, and that corresponds to preclinical stages of the disease where you do not observe anything, and then the disease becomes clinical. At which point you may report it, but not essentially not necessarily right away. And then the removal comes later. And so there's this not correspondence always between what's happening when you're modeling things and when you're reconciling your model with reality. And this is something that is true even at the without space. So I just thought I'd point it out here. I thought it was, because it's part of that paper, it's worth mentioning. Now, what Woolhouse, so I'm not describing the spatial aspect yet, although I'll say a word about this graph here. So we'll come back to this graph in a second when we look at spatial models. But I just want to point out this is something that will come up a variety of times later, and it's what is called a transmission kernel in the models of Woolhouse and collaborators. And a transmission kernel describes how the disease affects. So we are going to start calling them premises because that's how they are called in most of the models. So farms, if you want, how the disease spreads from one farm to another as a function of distance. And so here we're moving towards models where distance is taken into account explicitly. And let me show you one such model here. So this is a model of Keeling, who's also someone who's done a lot, and Grenfell plus Woolhouse. So these are very important people in epidemic modeling altogether. And so this is a model that they published in Science in 2001 about the 2001 UK pandemic. And here we see the kernel I was talking about. So I should make myself reappear. So what they're doing, and as I said, the models are space implicit in the sense that um, there's no movement of individuals. There's just an assumption that places that are located at a certain distance have an influence on one another. Okay, it is space is explicit in the sense that we're looking at distances, but it is implicit in the sense that there is no movement per se, just a remote influence. So here, what they do is they look at transmission between farms, and they say that this transmission is determined by the number and type of livestock and the distance between susceptible and infectious farm. And so this function here, what I want to show without making myself disappear, this function here describes the probability that an susceptible farm, I, becomes infected on a given day. And so you can see the components. These are a variety of factors. So this is the number of individuals of a given type, the number of animals of whatever type of livestock. And here you can see there's a sum on the other places. And what's important here is that kernel that I was just talking about before, which describes how the influence of a given farm or premise diminishes as distance from that farm increases. Just one remark in passing. I have a version of those slides on the website in the slides subdirectory that has annotations. And so if you're looking for specifics, you should refer to these slides rather than the ones that are posted on the main part of the website. If you go to the slides subdirectory in GitHub repo, you will see the annotated slides. Okay, so this is simple, so to speak. I should reuse air quotes here because parameterizing this model is quite complicated. But as I said, space is implicit here. And so what they do is then they conduct a lot of simulations and look at the results of the spatial model. And I'm not going to describe here yet what type of control measures they're looking at, because we'll come back to that. But you can see that they are looking at different control policies. So they look at the model that we just saw, this model here, but they can change some of those factors to take into account different control policies. And you can see that, so this is the standard model. And then they have IP, we'll see quite a lot in those models of livestock in space. This is infected premises. Okay, so this is what happens, for instance, when you're looking at a culling measure that only concerns infected premises. Then there's a prompt cull, there's an intensive cull, there's a 3 kilometer cull, there's vaccination as well. There's a variety of control policies, spatial for some of them. So, for example, a 3 kilometer ring cull means that you detect an infected premise, and once it is detected and reported, you move in and you cull all the livestock of a certain type, not necessarily all types, within a 3 kilometer radius. Okay. So there's a variety of techniques that are considered, and as a, let me make myself disappeared, as a result of these techniques, they look at how much cases happen, how many animals are culled, and how many animals need to be vaccinated for things to work. This is a, a bunch of graphs in this paper. So this here is the spatial distribution of infected premises. Um, so these were the red dots, and the black dots are those infected premises that were subject to culling, okay, during the 2001 pandemic. And then they performed a bunch of simulations, certain number of simulations. The graphs that you see here, I think they correspond to 100 simulations, but they did a lot more. Here you have, again, we come back to this kernel. Okay, this is the transmission kernel as a function of distance. Okay, you can see this. Uh, this is how the number of infected premises, so reported cases being the number of reported premises, uh, as a function of time in the simulations. This is the number of culls. Um, that result from the different simulations. And this is the number of simulated cases reported to 10 by 10 kilometer squares in the country. Okay, so this is real data. This is simulation data. And you can see space is implicit, but it's explicit as well because we know where all the farms are. And this is a computation of R0 from the computations that came before and shows you the value of R0. So below 1 is in gray, above 1 is in these varying colors, and they here highlight really the R0s that were greater than 1. And you can see, if you remember, when we looked at the epidemic, well, actually, even if you look here, but when we looked at the epidemic in an earlier lecture, we saw that a lot of cases were here, there, with some in Wales and some here. And you can see that their simulation model shows then that the R0, yes, was indeed probably very high in those regions. And in particular, here you had values of R0 that were really large. Another model of Woolhouse, again with Keeling in this case and Hayden. And here this deals with control policies in neighborhoods. And by neighborhoods, they mean nearby farms. Okay, so how do you control a foot and mouth outbreak when you take into account the nearby places? So this model is very much a Kermack and McKendrick type model with some interesting variations, uh, which I'll point out now. So first of all, there's this F of C here. C is the intensity of the control effort by authorities. And the purpose here is to look at how the system reacts to varying levels of control effort. So if f of c is 1, you can see that what's happening is that there's no local transmission here. And a lot of so okay, let me so if f of c is 1, then there's no transmission from, or no new transmissions, but you're also uh, removing some premises. So you're taking all the susceptible premises that came into contact with infected premises, so the exposed essentially premises, but you're not allowing them into the infected. You're automatically removing them. Okay. So that's an effect. It's a caricature, but it's a caricature of what it means to be uh, controlling the disease at the local level. So you're taking an infected premise and you're moving it directly into a removed premises, whether that is through vaccination or through culling, you just move them here. Um, they compute, so for a given value of C, you can compute the basic reproduction number and a controlled reproduction number that depends on C, but is simply smaller, typically, than the original reproduction number, and that is telling you how the efficacy of your measure is working. And I'll point out this is very similar to what you observe when you are considering a vaccination model. This would be exactly the same vaccination within a population. This would be exactly the same characteristic you would get if you were looking at a model for vaccination in a single population and you were vaccinating a fraction P of the individuals, then you would get that the controlled reproduction number would be 1 minus P times the original reproduction number. They take this model and they consider a metapopulation version of the model afterwards. And so what they do is they look at clusters of holdings of the farms, okay, and they break the population down into subgroups where there are subgroups within which short range transmission can happen and between which long range transmission can happen. And the idea is that you can then try to look at whether it's better to control things at the local level or try to minimize the long range spread. They have different groups depending on where you are in terms of transmission, local or global, and they study this. I think this is the last Woolhouse et al. Paper that I'm talking about, I believe. This is a paper that appeared in Nature in 2003, so 2 years after the 2001 pandemic, epidemic in the UK. And this is about modeling vaccination strategies. So what they have is they start with a spatial model. So this is not a metapopulation type model, but it's quite similar in a way. What it does is it looks at the infectious state of every livestock farm in Britain, and they try to predict the daily probability of infection. And so there's a rate at which a farm that is currently susceptible is infected, and that depends on the interactions of, so this is the local farm, okay, so livestock of type L in farm I, so this is the farm that they're interested in. There's a notion of the susceptibility of the livestock that is there, and then they sum over all infectious livestock farms and over all types of livestock. And again, this is the same type of function we saw in the earlier model. You have TL, that is the transmission rate for a given livestock, the distance between farms, and the transmission curve. And what they do is they assume that an infected farm incubates for a certain number of days. That's before it becomes detectable. Then it is infectious. And then 9 days after infection, this is a model, so we're taking a standard number, let's say. 9 days after infection, the presence of the disease is reported, and then there is some I was going to say fuzziness, it's not fuzziness, but there is some degree of variation in how long it takes authorities to move on the knowledge of infection. So they assume that it's 1 to 3 days, and then culling happens. But here they're interested mostly in a problem to do with vaccination. And here, so this is a schematic of what happens. Um, so essentially, you have an infected premise here, and then you have distances from there. And the idea is that it's likely that those farms here are already infected, because by the time the that infected premise is reported, those infected premises here are very close. And so here the idea is, where do you need to vaccinate? And for that scenario here that they're considering, they're saying, well, the vaccination should probably affect those guys, because by the time things are reported, those premises are probably already infected, whereas those have a lower probability of being infected, and so they become the highest priority in terms of vaccination. Okay, so now I'm going to talk about a model of Ringa and Bosch. So that's someone who was at Guelph, and Chris is now in Waterloo. And Notice was a student of Chris's. And I want to point this one because you will see quite a lot of work using this type of model. So I thought it would be interesting to point out that this type of model exists. So this is a foot and mouth disease model again. It's again a model that uses premises, not the number of infected livestock, but the number of infected premises, well, of premises with different infection statuses. Um, and here the model is for endemic countries. So these are countries, if you recall, in an earlier lecture, I was talking about the different levels of of control in a country. We're talking about countries that are lower down in that control ladder that I was mentioning. Now, what's a pair approximation model? The idea of a pair approximation is that you're looking at pairs of elements. So, for example, you have two farms, or several. You have several farms, but you suppose they can be in status X or status Y. So, for instance, here this is an epidemic model. We look at susceptible and infected premises. Um, and then what a pair approximation model does is that it considers the expected numbers of such pairs. So is there, and if you're thinking, this is when you're looking at graphs in particular. So you would be looking at a graph where one vertex on your graph is, let's say, a susceptible vertex, and near connected vertex, one vertex connected to it is an infected vertex. And you want to know what's the expected number of such connections, where I have a susceptible and an infected vertex connected to one another. Okay. So I'm going to show you how you derive that, and I'm following their paper. Okay. How you derive that for the SI edges. So what they what you do is that you consider that the dynamics of a pair involving an S premise and an I premise, it's governed by an equation like this. So here, for example, G prime, G of T is the expected number of SI pairs. And so that variable evolves by taking the sum of all the events of type epsilon and the changes to the number g of t. Okay. So what we're going to do is look at the transformation of edges. So for instance, if you think about an SI edge and there's an infection resulting in that from the connection of an S and an I. I should make myself reappear. There's an S and an I. Okay, let's say this is S, this is I. That edge results in the infection of my S. When that S becomes unexposed or latent. Okay, I prefer the term latent, but so this we will denote that way. An SI pair becomes an EI pair. It's transformed to an EI pair because the S component in that pair has become E because of the infection. Okay. So now if you think of an SI pair, what can happen to it? Well, this is the list of things that can happen. An SI pair can lead to an infection of a susceptible form by the infectious form in the SI edge. Okay, so that means that's that thing I was just talking about. SI becomes EI. And in terms of the expected number of SI pairs, of course, this is going to diminish the number of SI pairs because it is destroying one of those SI pairs. Okay, so that adds a minus tau times the the expected number of SI pairs. Okay. Now you can also have triples. So there would be infection of a susceptible form from the left, if you think about it, in a triple. So I would have in this time I'm considering two infectious forms, and in the middle I have an susceptible form, and in that case it's the left one. Okay. This is my right hand, the left one on the slide, but it's the left one that contaminates the susceptible. Okay, so this means that, okay, so here you have I goes to SI here, and so, oops, this is disappearing. So again, you have a minus tau SI. Then you can have a latent period, that creates, okay, because I had a pair, an S and an an S and an E that became an E because of contamination by another edge. Okay, so that E here becomes an I. So that is because its latent period is over, and that creates an SI. You have recovery of infected farms, okay, recovery or cutting. So here, no, he's looking just at vaccination, so recovery. So there's a recovery at a given rate sigma, so that means the SI edge becomes SR, and that is the rate sigma. Then there can be ring vaccinations, okay, ring vaccination in triples, um, loss of natural immunity, which in that case results in the creation of a new, I should say, well, it's an SI pair, but it would be IS here in this case. And there's also loss of natural immunity. So this is, and I should point out, so these pair approximation models, they, in the end, the model, and I'll show you the model in a second, in the end, the model is very similar to classic models, except that you track much more variables because you're looking at the pairs. Okay, I'll come back to that. But in terms of the SI prime, so how does the expected number of SI edges evolve? So in terms of what I was just saying, there is formation, there is loss because of these triple pairs that become uh, I, I. There's loss because of a double pair that just becomes EI. Uh, this is creation because of the end of the incubation period of this part of the pair. This is loss because of what is it? Sigma. I can't remember where was my sigma recovery simply. And these are ring vaccinations, and you can see the ring vaccinations affect both the SI pairs. I mean, the rate depends both on the SI and the ISI. Uh, and then there's the vaccination here. Um, where is it? Oh, I think no, no, here. So this is ring. Where's my P? Okay, I've lost my P. This is the other type of vaccination. Okay, but you see the idea. So this equation is more complex, and than what you would typically assume for an SIR model or SIVR model, but it boils down to the same thing. As I said, this leads to models that are more complicated than the ones we have. So if I had an SEIRV model, I would have 5 equations, but as a pair approximation model, I have a lot more because I have those, but I also have the pairs. Okay, and I have more pairs, etc. So this leads to models that are one of the advantages is that you can use them to consider on graphs. For example, that's a different modeling technique. Graphs in general, I should say. Okay, so where you're considering connections between farms. So that's why this is useful here. Just in terms of the analysis, I'll point out, I won't spend a lot of time on this, but the same type of analysis as you would carry out on a classic model also works here. You can derive an R0 value. Uh, you can define an R0 value in the presence of ring vaccination as the only control measure, or you can have prophylactic, that was the 5P prophylactic. So ring vaccination takes place after the fact. Prophylactic vaccination takes place before. So this, you can derive a basic reproduction number for here. And if you have both prophylactic and ring vaccination, you get an R0 that is complicated. But I mean, if you were looking at similar model with space added in a sense, you get also a complicated expression for your audio. Okay. So here, space is there because those pairs that we're talking about, they can be, as I said, so they can be the nodes or the vertices in a graph, in a network. So that allows me to look at how those premises are connected, therefore spaces in there. And here you can see, for example, a study of the value of R0 as a function of the intensity of prophylactic and ring vaccination that's taking place. And you can see this is a weird. Remember that to make those slides, I'm inverting a lot of the colors, so you can see that the low values have high white intensity and they're here. And then as we move this way, so you're going down in our zero values here and up in our zero values as you move that way, which is typically the opposite of, in terms of color, of how we would present things. The next model I want to detail is one by Cabezas et al. Um, here. And it's a metapopulation model of foot and mouth disease transmission. And here, this is specialized to the United States. It's a very practical model. Let me get into it. First of all, same remark as I made before. There's a variety of stages that are considered here. And remember, I pointed out with the first paper of Woolhouse that there was a sometimes discrepancy, well, not discrepancy, but when you're thinking about the data itself, it can be quite complicated to understand um, what how to match the data you have with your actual model, and this is something that they point out here as well. And they have a number of compartments that I'm going to highlight, but these are essentially the compartments in their disease model. Susceptible, latent, infectious, and non-infectious recovered. But in terms of the disease progression, uh, things don't need to match exactly. Now, the model uses a certain number of variables. So they have susceptible, latent, and they have three infectious compartments. They have two that are subclinical. So before you actually see symptoms, and then they have clinical infectious. They have clinical, but no longer infectious, and non-infectious, clinically recovered. And that's quite interesting here. Uh, this the equation for S and for L, equations for S and for L are not trivial. So let me go through this a little bit. So this is a differential equation, but you can see that there is a switch that depends on the state of the system. Okay. So some of those components, so first of all, there's a binomial variable here that depends on, I'll come back to that, the phi at time t minus 1. So this is essentially, it turns out to be a delay differential equation. They're looking at 1 day prior because of the time to detection. Okay. But there's a binomial variable in here. There's also, as I said, you can see there's a lot of switches here. So the model equation depends on the system state, which makes for a very complicated model. And I should point out this model is used here as a simulation model. If you were to try to analyze that type of model mathematically, I think you could probably set aside many years of your life because this is complicated. Okay, this is a switching system that on top of that has switches that are non-trivial. So this is a complicated model. But from a simulation perspective, it's completely doable. You check what the state of the system is, and there's a lot of checks that must happen. And I'll show you later that they actually conduct quite a sort of in-depth sensitivity analysis. But I wanted to point this one out to show you how complicated a model could be. And that's for a single population. Okay, we are going to soon put this in a multiple population context. As I said, the L equation is because upon infection, susceptible become latent. And so the L equation matches essentially the S equation. It's equally complicated, but those terms, if you check them, correspond to the ones here. They just indicate that susceptible individuals flow into the latent compartment at a corresponding rate. For the other compartments, things are a bit simpler. Um, you can see the two subclinical infectious, I1 and I2. I3 is clinical infectious, C is clinical non-infectious, and R is recovered. As I pointed out, you can see that there is a time delay here. So this is the state of I1. This notation is a little non-standard, but I followed the one in the paper. Uh, this is I1 at time t minus 1, etc. Okay. So this is the model that they consider in general, but then they put it in a metapopulation context. So not only is that model, so that's essentially each one of those so-called pens, which are let's think of it as a building, uh, or or an enclosure on a field. Okay, so these are the different locations, and each one has a certain number of animals. So each one of these pens undergoes disease propagation locally, that is driven by that model, but they're also coupled to each other through a variety of mechanisms. So typically, transmission within a pen is it can be airborne, it can be water borne, etc. But then there's transmission between pens by, for example, animals coming into contact. So if you have two fields, they're separated by a fence where an animal might come into contact with another animal because the fence is shared between the two enclosures. Uh, there's contaminations of all sorts. So this is what the model essentially looks like. And there's also a pen, like an enclosure in which you can put the contaminated animals or the suspected contaminations. And there can also happen contamination. And so if you're looking at the model itself, this looks at the transmission. This is a metapopulation model, as we've seen in the previous lecture, where, for instance, the number of susceptibles and latently infected individuals in a hospital pen that are infected as a function of the number of animals who come from other pens and are put in the hospital pen, and etc. And so, as I said, this is a very complicated model. It's analyzed only numerically, analyzed quite extensively numerically. So what they did is they considered a variety of situations. They have small herds, medium-sized herds, and large-sized herds. I mean herds, farms. And you can see here, for example, FS1 is 4,000 cattle, feedlot with one hospitalized pen. FM1 is how many? 12,000 and one hospital pen. FM2 is, well, if you have more hospital pen, etc. And the large ones are 24,000 with one, with two, and 24,000 with four. So these configurations that I was showing here, you have a different number of pens, you have a number of hospital pens. And so what they're looking at here is, for example, the percentage of cattle with latent infections. Um, depending on time. And so this is cattle and home pens and etc. So we're looking at how these things evolve through time. You can see the percentages. Um, and yes, these are the percentiles in 2000 outbreak. So you can see this was studied numerically quite extensively. It's an interesting paper. It's very, very complicated, I should point out. One thing that is really nice that was not done quite as often, and what I think is good to carry out, they are looking at the correlation, what's called the Spearman correlation coefficient value, which is used often when you're doing sensitivity analysis. So we are looking at between the model parameter values and the outcome variable. So this is a sensitivity analysis, and they carried out a quite thorough sensitivity analysis. I think it's worth taking a look at. Probably it's worth taking a look at in a simpler context if you are going to use this type of thing, because this is quite complicated. But it's done here. Another model I want to look at is a model of Brad Hurst et al. Um, Here, this is a hybrid model, and I mean this presentation as a way to introduce a variety of modeling techniques. And here you have something that's quite interesting. It's called a hybrid model. This is from 2015. And this is considering spread of foot and mouth disease in Australia. So the model used here is hybrid. Hybrid means combination of models in a sense. And here what is being done is that they use an ODE model for within herd spread dynamics. Okay, so they look for each herd, they look at an SLIR model, a classic one. Okay, so they have birth and death. You can see that the total population, no, there's death due to the disease. No, 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 no. So it's the total population follows a nice behavior, mu minus mu n. And this is a very classic SLIR model. But what's interesting here is that this SLIR model is used within the larger framework of an agent-based model. So what they do is they use data from ADIS. You'll see later ADIS, I don't know how they say that, which is the Australian Animal Disease Spread Database. Well, the Australian Animal Disease Spread Task Force or something, but they have data. So this is what's used to model spread within a herd, and then each herd has, they call this an equation-based model, which is that model I was showing just prior. But then there's a stochastic model, which is an agent-based model that establishes how herds are connected. Okay. So uh, each herd is a system of ODEs, those 4 ODEs, and then there's a stochastic ABM agent-based model on top that is connecting them. And it's connecting them with things, for instance, such as wind direction. So this tells you, as a function of the wind, how far downwind the propagation takes place. So this is for a pig herd, for example. They're looking at a certain distance, and you remember that this is tied essentially to what we saw with the wool house dispersion kernels. So this is exactly what this is doing, except that here there's a notion of direction of the wind that is added, which is easy to do in an agent-based model. If you have records of how the wind is blowing, you can incorporate that and do your dispersion kernel that way. And so they have extensive data. So you can see that they have a number of farms of different types. These are all the farms used in this Australian database was talking about. And so they have farm size, herd size, and etc. They conduct some analysis. In that paper in particular is not so much interested in the analysis as in the presentation of this system, which is used by the government there, or by some corporation. I never really know who's what, uh, but this is this. And the last, oh no, two more. uh, Another model I want to talk about is a model by Brunner Kemper et al. So this is a model on the spread of foot and mouth. Well, I mean, this is more cattle disease in general. It doesn't have to be foot and mouth, but I thought it was linked interestingly, and this is in the United States. I'll point out this was published in 2014. It's not apparent there. And what they use is what I'll call the interstate certificates of veterinary inspection data in the US. So the they consider it's a very interesting model, I should point out, but it's also extremely extensive as well, a bit like the former one, the one we were just talking about. There are a variety of transmission routes that are incorporated in the model. You can see there's shipments, there's spread between fence line contact, cross border, that's the same. There's spatial scales that I'll show you in the graphs. So they'll look at um, all the counties in the US, or they'll look even at the US in general. Uh, they look at data, as I said, there's a variety of data sources, and some uncertainty that is considered. The model parameters, I'm not going to spend some time. I mean, it's a, as I said, a complicated model. There's transmission on different premises, spatial kernel. There's a so no non-movement. Uh, there's a scaling effect on the of premises size. There's a variety. It's very complicated model, but I think it's really interesting. You'll see in a second. So one thing that they've looked at, for example, is the state to state. So this is really model data-driven modeling. They have this wonderful data set, and they're looking to use it. So this is how cattle move between different US states. Um, So there's two different. So this is summary data given by a certain organism, and this is sampling of those ICVI data that I mentioned at the beginning. Okay, so and they use mostly the sampling method, sampling of 10% of the data. So what they have is if they look at um, how connected the farms are, if they look at the state level, all states are connected to one another. This is so we call this a giant, strongly connected component. That means every state here has cattle going to every other state. Not necessarily directly, okay, but there is a connection. There's a little problem with New Jersey. But the problem is not because their cattle do not access the other states, but more that they did not provide that ICVI data. Um, so the data is unknown for New Jersey. Uh, and here, this is what happens when you look. So the strong component is the orange one. And so this is what happens when you look at the county level. Okay, there's about 3,100 counties in the US. And so this is looking at all those that are in the orange color are connected to each other. Okay, they're part of the same graph, and the others are outside the component. And for those that are gray here, there's no data. Okay, so it might not be that they're not connected, uh, but simply that they are not, there's no data. Um, oh yes, I should say so. The brownish, what was it? Okay, now that's the in degree, out degree, sorry, the distribution of out degrees. So the out degree is the number of other locations that a location is connected to. And again, they look at the data both at the state level. So this tells you, for instance, that, and yeah, remember that because I'm inverting my scales, the light colors are the high values and the darker colors are the lower values. So something with a light color has a high out degree. That means it sends, for example, if you look here at Montana, it sends cattle to a large number of other states. Okay, that's what the out degree says. And this is the same measure, but at the county level. And so, of course, you can, at the county level, there's more local local connectivity happening. So this is why you see that those colors are darker here because a given county will not send to all other counties in the US. Um, this is the same, but for in degree. So same light color means receives a lot of cattle from other locations, other states in this case, and other counties in this case. Um, So same, you can see how this way they get a sense of how cattle movement is happening. And this is quite interesting. Uh, One remark in passing, if you compare this to what happens with human movement, this is very dissimilar. And this is indicative of what is happening in terms of cattle husbandry, in the sense that um, the movement is quite directed. Okay, so you can see this, for example, has high out degree, but it doesn't have such a high in degree. So it doesn't mean there's a lot of movement like this. It means they probably raise younger cattle and then send them out to other places for later stages of raising. Um, This is the extent of the epidemic. This is simulations, okay, simulation results, and this is looking at epidemics spread throughout the United States in a different level of movement scenarios. So, for example, A and B assume that movement is normal. So that those graphs I was showing you before, they're unaffected. You're looking at them as they are, and this is what happens in terms of the spread. Uh, those two here, C and D, assume that there is county level movement ban. And those two at the bottom assume that there is state level movement ban. Okay. Um, and you can see so that the behavior is quite different depending on the type of measures you take. Here, just to show you, this is a movement versus local spread, and this is principal component analysis in terms of what, in terms of so they analyze their results using a PCA, which essentially looks at the out degree and the density of premises in a given location. And this here shows the places that have the most propagation. Okay. Okay. No, I don't have it. Got it. Okay, and finally, you have to move on in terms of time, otherwise this video is again going to be very, very long. This is a model of glass and barns. This is again a model by Australian people. And this is people based in Australia. I don't know if they're Australians, but they're based there. This is an interesting model of, again, it's not specific to foot and mouth disease, but it's infectious diseases of livestock. And this is again looking at intervention policies and their effect. This is a stochastic model. It's a very cool model. I won't get into the specifics of it. It's a metapopulation model explored stochastically. I won't get into details, but we recommend taking a look. So this is what happens in terms of the model scenarios. So at the top here, you have the model in terms of what happens without control. So the squares are high density regions, the circles are low density regions. What distinguishes them is their local mixing rate. So this is a stochastic model that looks at how the infection is generated. I recall it's might anyway, so what's important here, you have a lambda L, yes, we can see it, and here a lambda H. Those lambdas represent the rate of mixing of individuals within those regions, and they vary. And then there's also between region mixing, and those are these diamonds that you see here. And those between region mixing, they represent the how things interact between regions. And now, if you drill down into the lower level, you can see that there's different types of vaccinations that are considered. So there's two types of vaccinations and two types of control measures. So homogeneous vaccination, you're simply vaccinating, these are those top two here. Homogeneous is this one, vaccination is those two. Homogeneous vaccination, you're homogeneously vaccinating in high density regions. Heterogeneous vaccination just means you take one of the high density regions and you vaccinate there, but not necessarily all high density regions. Quarantine is you impose some time on the movement of individuals between regions. Okay. And banning of high mixing events are simply so these are farms or markets or sales, etc. And so in banning high mixing events, you just forbid access to these regions where the high levels of mixing is taking place. And so they've looked at a variety of scenarios. So here you can see this is the in the rows you have the rate of mixing in the high density regions, so increasing mixing rate, and then different types of vaccine efficacies. And they have homogeneous vaccination and heterogeneous vaccination. And these are the regions which lead to the disease being controlled under those regimes. So you see that homogeneous vaccination always, because I should point out, so the that region also extends all the way to here. Okay, so this region includes both regions, whereas that region here includes only the white region. So in all cases, homogeneous vaccination here seems to do better, but you can see how this depends on. Remember, mu is the mixing parameter in the in the events of those diamonds, and so if the this shows you sort of how the vaccine can help here. Um, This here is for two, again, different scenarios of vaccination, of mixing, and how these are combinations of P1 is the proportion of the primary cases that occur before quarantining is in place. Okay, so this investigates if you have reactive quarantine, how that is going to affect the propagation of cases. These are the elimination regions again. Okay, so this is the larger the elimination region, the better in terms of control of disease. Okay, and that's so. As you've seen, there's a variety of approaches that are considered. Um, some of the control mechanisms are spatial. They deal with, and I should move on to just to point out this. This is the review on foot and mouth disease. So some of the control measures have to do with controlling the movement of animals. Some of the movement control measures have to do with culling in certain regions. There's also vaccination that can happen, and vaccination can be local, or it can be it can have a certain spatial configuration, and there's a variety of other models that you could look at. I didn't review them here. The domain is quite rich. Okay, and now I want to move to avian influenza. That will be a bit shorter, hopefully. I'll start with a model of Bruiba and others. So this is Bruiba, Gurley, Liu, Takekawa, and Wu. It's a model it was published in 2015. I shouldn't say it's a model. I'm going to start with this because it's a review of spatial spread of avian influenza. It's quite a nice paper to look at if you are interested in that aspect. Um, what they're interested in here is really the spatial temporal spread of this, and this is mostly for migratory birds. But so you can see that this is a typical year. They're looking at northern hemisphere birds. Of course, things might be a bit different if you look at other places. Uh, but there's spring migration. For us, for example, here in Manitoba, we've just received our yearly arrival. I mean, they arrived somewhere. They start arriving there. Canada geese, in particular, have started popping up all over my campus. If you've ever dealt with Canada geese, you know that this is an interesting moment. Uh, they're currently breeding, which is why it's so interesting, because they just take their space somewhere and lay their eggs and they will defend them to death. But so this is what's happening right now. Then there's maturation and molting, which is when the youngs prepare for the migration that's going to take place. And then finally, autumn migration and wintering, which, for example, for North American birds, typically takes place in South America, Brazil, a lot, but also southern US. I mean, it doesn't have to be across to the southern America. It sort of depends a little bit. But okay, so and that's how the movement, the movement and the activities organized throughout the year. So, for instance, here this is a map showing the movement of bar-headed geese, and this is GPS tags. Um, and what it's showing you is where they are. This is not indicating time, but you can see where their location is. Uh, as a function of, well, I mean, it's throughout the year in this case. The time period is not indicated, but you can see that they move quite a lot. This is China, so China being a very large country, they come all the way from this must be the border with Mongolia, which is a very cold area, and then all the way to southern India, which is much hotter. And that's several thousand kilometers here. Now, if you're looking at a patch model of this, then you're going to need to incorporate this movement. And that's quite different from the models we saw, first of all, in the earlier video on metapopulations, and just now with foot and mouth disease. Here, there's really a periodic component. So if you're thinking about how birds move between locations, you have to incorporate this graph that we were just looking at that tells you at what time in the year the individuals do what. And so if you're thinking about them, so if they're at their wintering ground, which is located somewhere, then their spring migration takes them somewhere. They might stop along the way. So if you go back to that bar geese, so that's probably where it spends its summers, and that's probably where it spends its winters. And in the middle, they are still making their stops there from time to time. And so you have these stopovers on the way from the wintering site to the breeding grounds. And then same thing, stopovers during the fall migration back to the wintering grounds. Okay. And the activities are different because that's where the birds are born. They're not born here. So you see there's some components that are going to be quite complicated. And so a model would look at something like that, for instance, where you would have these different patches and or locations, and oops, I should make myself reappear, and you can see that here, for instance, uh, during the movement, that can be, and here we're looking at, so for example, cross-contamination. These would be M would be for migrating birds, and P is for poultry. So as those migrating birds are migrating, they might come into contact with poultry, and that's where the local infection by avian influenza would take place. So as I said, I mean, there's plenty to look at in this paper. Recommend it, taking a look if you're interested in this aspect. Second paper is a paper by Nick Baksh et al. It has to do with a metapopulation model for HPAI, and here they're looking at control. Okay. compartmentalization, and I'll explain that in a while. So they're looking at poultry farms, uh, and here their object is to say there is, when you look at the poultry industry, there are big players in there that typically own quite a lot of farms. And because these companies have processes in place, they tend to be more integrated. Uh, and so, in a sense, this paper, what they want to consider is what happens if you exploit, you try to take into account this, and that you may have, you think about this not only in terms of, oh, I'm going to restrict movement to try to prohibit spread, but I'm going to exploit the fact that I could talk to a company and try to get them to do things. Okay, so these are the repartition of poultry companies. Okay, and what they are doing is they are looking at the centrality, what we call the degree centrality. It's normalized. So the degree centrality is how many, well, we saw out degree and in degree before. This is not considering orientation here, but this is looking at what the out and in, what the degree, so how many other places a given location is connected to. And this is normalized, so it goes between 0 and 1, um, not in terms of the actual degree. And the vertices here that you see labeled here, they also have high betweenness centrality. Betweenness is another measure of graph connectivity, which indicates how many of the other places have to go through you to get to other places. So vertices or nodes that have a high betweenness centrality are very central in the sense that other, so for example, if I'm here and I want to go here, I will have to go through one of those places. That's what the high betweenness means. Okay. And the line widths here represent the number of slaughterhouses that are involved in the relationship. So what they're doing here is they're looking at a metapopulation model uh, that's also a group model, essentially. They have population of two types. So rho is network core group, and population 2 is network periphery. So the core groups would be those vertices here, and the periphery would be the others. Um, and they have also multi-site and single-site premises. Okay, and then there's force of infections acting on those. Oh, I'm missing an equal sign here. This is of course I prime equals S rho J. Um, so they have force of infection. And then what they do is they consider, depending on whether they're in the network or the core, they have something like this. So they have single sites and multi-sites within both types. Remember, this is the inner part. These are the highly connected central nodes, and these are the less connected nodes. And so within the highly connected nodes, we have single sites and multi-sites, and within the peripheral nodes, we also have multi-sites and single sites. And there's movement from the different types of sites and between the core and the periphery. And so, for instance, if they're looking at multi-site premises within the core group, there's a lot that acts on those multi-site premises. So these are the force of infections, and you can see that they involve So there's density dependent and density independent transmission rates. There's weights on the transmission for the different types of sites. There's a weight of connections. There's whether things are connected or not at all. But there's weights, those omegas that you see here, for example, they're the weight of transmission. And so in each of the multi-site sites within the core group, the force of infection, so the incidence, looks something like so. And what they do is they look at two types of control mechanisms. And so that's the main objective of that paper, is to investigate the difference between two types of methods. So one of them, and that's the most frequently used one, is what they call zoning. So zoning is that they say, well, there's geographical boundaries that separate parts of a territory or country, and so they will have, for instance, control zones restricting the movement of animals, and for instance, uh, enhanced biosafety measures. Um, and so they allow within population movement and between population links. And then compartmentalization is then the same as zoning, but they don't look, it's what I was saying before, they don't look only at pathways that have to do with the geographic proximity of units, but they also look at within company integration, because, as I was saying before, it is expected, and not only expected, it is known that movement will happen preferably within a company. And so when they do that, that means they consider two types of approaches. So zoning is that first one, where they will allow movements mostly within regions and impose large control measures as to the movement between regions. Whereas in compartmentalization, the movement can be longer, but it deals with uh, companies, sorry. It's things that happen within a company, and typically they would not allow further movement. And so what they find is here. So what they study is how these two mechanisms act on the risk of infection spillover. And so here, for instance, they represent the relative risk of infection spillover when you have compartmentalization. And so the light area there on the left is the additional risk of an outbreak when you have compartmentalization. And the dark area is the one, the additional risk due to zoning, when you're using zoning as a mechanism. And I should reappear. Okay. And so this is as a function of the interaction strength between premises and the transmission rate. Here, they're looking at how these thresholds vary as a function of interaction strength and transmission rate, same as before, but how things vary as a function of the coupling strength. Okay, so at the top you have, for example, the compartmentalization leads to an increase here of the risk of uh, you see. So if I have these are the different these are the couplings, okay, between multi single site, multi site, and etc. And so what you can see is that as you uh, reduce these coupling, you go up. Okay. I'm not going to go into detail. It's not an easy interpretation. I really refer you to the paper for more detail. But again, this is a very interesting stochastic paper. I'm getting lost a little bit here in this is a long lecture. Uh, I refer you to the paper for detail. Um, what's really interesting is this consideration of the effect of the different control techniques and how it increases or decreases the risk as a function of the type of methods that are taken used. A quick words about a paper by a French group, group based in France again, that has to do with H5N8 in the southwest of France. And again, this is control strategies. So, in terms of what happened, uh, this is 2016 and 2017, and these are the number of infected premises in terms of the date at which they became suspected of being infected and the different measures that were taken. So you can see that that first line here is when they started preemptive culling measures, and that second dashed line here is when they took additional measures. Here, this is a bit the same type of model as we saw before. This is a stochastic model again. It's a space-time survival model. This one looks at the survival in different states. Um, and I've included the model here, but I won't detail it too much. I'll point out that again, you can see that the coupling, and I should, there is a force of infection, you see, so I on J, and that is going to be where space becomes important. They then vary the transmission rate as a function of time because they want to incorporate these three different periods in the epidemic. So they have three different transmission rates. And one point worth noting is yet again this idea of timing, which I think should be really at the back of your mind when you're looking at this type of problem. So here, what I'm showing you, or what they are showing you, is that when you're looking at the number of infected premises that are detected, it really depends on the type of surveillance that you're taking, you're conducting, um, and the timing of observation is very different from the timing at which events, well, not very different, but there's a lot that you don't know. So, for example, if you're looking at passive surveillance, what's going to happen is that between the infection of a premise, a farm, and it's becoming infectious, there is this latent period L here. And between the infection and the symptoms, there is this incubation period. So this is the duration of the latent period. This is the duration of the incubation period. But when you start seeing symptoms, this is the first time that you know really that something is happening. Before that, you have no clue. Okay, so the red pinkish events here, they're the ones that are observable. They're observed, whereas those white ones, they are not observed. Okay. Um, so that's, if you're doing passive surveillance, that's essentially what's going to happen. And if you preventively cull infected premises, then that time, of course, to culling is going to be much shorter, but you don't know actually if, effectively if you have an infection, but you're doing it preventively. Okay, so the confirmation of infection is done on the dead animals, and you will see whether they were infected or not. But that time to culling is the shortest in compared to the others. Uh, but still, those are events you don't know. So they might, in this case, this is preventive. So this is not necessarily true, and that's where the confirmation comes. But you might have infection and infectivity, but at that point you're cutting, and therefore you're preventing that risk. Um, and finally, if you have active surveillance, you're somewhere in the middle. Uh, you have potentially infection and infectious infectivity arising, but then at some point there's suspicion of infectivity, and you go into curry. So what they do is that they consider the model, and because it's a stochastic model that's based on the data that they have, etc., they're able to compute, for instance, a reproduction number as a function of time. This is when you're below one, you're expecting the epidemic to essentially go away. Which in passing you can see that here it's not going away, but that can be because of space. And here this is how far away the infection went as a function of the farms that were infected on a given time. Okay, two last models that I want to look at. One is by Fournier and collaborators, and it's about looking at rest days in live bird markets. And so by rest days, they mean days in which the markets are not subject uh, to further inflow of birds. So they have a very simple model originally. I point out a simple model is really simple, and then it gets complicated. So they assume that there's two routes of transmission. There's direct contact between the animals, or there's environmental contamination. They have an infectious period, which is denoted Tinf, and so the rate of transmission times Tinf tells you what the force of transmission by a single individual. Um, and for the environment, there's other parameters that come into play, one of them being how long the pathogen stays in the environment, and etc. So you can compute precisely, I have it here, you can compute the value of the environmental transmission. Now, if a population size doesn't change, as large enough, and the infectious period goes to its end, that means you don't intervene, uh, then you can compute a reproduction number that is simply essentially the force of infection through contact plus the force of infection through the environment times the number of animals that are present. You can look at how much of a contamination comes in through the environment through this ratio here. That zeta is the proportion of infectivity that is a consequence of the environment. So it's simply this quantity here. And well, this is typically something that is estimated by other means. R0 you might have some clue about, so you can compute the beta and the eta that are required. Um, what they do is that they look at a stochastic infection process. Okay, so they take this very simple model, they put it in a stochastic context, and consider what happens. And so at the level of a market, what they would have is something like this. So here, this is the probability that a bird that's introduced here is still in the market. Okay, and so there's when the market is open and the market is closed. So when the market is open, the bird might be sold, and that's why its probability of being in the market decreases during that time. When the market is closed, the bird stays there. If it's staying there, it can contaminate other birds. Otherwise, the infection goes somewhere else. And within the market, these are the different components. So here the animal might be sold and slaughtered. There's contamination through the direct contact route. There's contamination through the environmental reservoir. That's the average, the distribution of latent times. So latency is quite short in HPAI. So that is, you're assuming that individuals cease their latency mostly after less than half a day. On the other hand, infectivity here lasts on average 2 days essentially, and is distributed this way. So that's what happens within a market. But now their issue here is to look at what happens in a system with markets, and many farms. So what they consider is a meta-population model, where they have a wholesale market. So this is like a big market that sells animals to not really to the end user, but more to the farms and etc. And that wholesale market moves poultry to the regional markets, and the poultry itself goes from the farms into the wholesale market. There can be some movement from farms to smaller markets, but there's also movement, longer range movement to the wholesale market. Then there is movement between the farms, the different farms. There is sale of animals to the farms from the regional markets. And as I was saying, there's also movement of animals from the farms into the markets. So what they use to consider this model, to write the model, sorry, is, as I said, it's a stochastic model. So they compute the number of susceptible birds in a given farm I in a given cluster. Because, of course, the clusters depend on a given market more than other markets further away. And so that number of susceptible birds is subject to a force of infection that is written like so. Okay, that force of infection uses an instantaneous hazard rate of infection. This is the instantaneous probability that an individual will become infected, that an event. I mean, if you think about hazard rates in general, this is the instantaneous probability of an event taking place. So here, this is the instantaneous probability that an individual bird will become infected there. And that hazard rate, you can see, involves the number of infected birds in the location, but also, for instance, the coupling strength with the different markets and farms that are present. Okay, so this is a complicated term. So that delta here, you can see, depends on all these different components, and those components depend on coupling between the location. So again, movement is implicit in the sense that we're not moving chicken around in the proper way, but the influence of space is encoded very precisely through this term here. In a regional market, you can do the same computation, and here the hazard of infection is given by this term. This gets quite complicated, as you can imagine. But they consider simulations here, and they're looking at, remember, these are the open and closed period, or vice versa. I can't remember which color. Open is pink. So yeah, open and closed period of the markets. This is the prevalence of infection in the market under several scenarios, depending on how long you close things for. Um, so how often you introduce a new cohort in the market, so they can study all these different scenarios to try to see if there are some that are better than others. And the last model I want to talk about briefly is a model about Korea. It's by Lee, Ko, and Jung. It's a recent paper, well, relatively recent, from 2019. And here it's about the spread of avian influenza again in Korea. So they're looking at the center of Korea, the central region of Korea, and in that part of Korea, they're looking at these districts. And these districts also contain a certain number of towns um, and a certain density of farms. So I wanted to finish with this model because this is it's a much more classic version of a metapopulation. It still does not explicitly describe space. I mean, movement in space. It describes space explicitly in the sense that, of course, each one of those eyes corresponds to one of those regions. And so for I from 0 to 15, you have different regions that are represented. You see, this is an SIR model, very classic SIR model. These are the infection terms. This is, sorry, this is movement. Um, yes, um, control, I think. And so, yes, this is infection here. Yes, it's got a minus here. This is infection. I'm missing a minus here, I believe, because typically this is the dispersion kernel. So this describes how location I is connected to location J, and that force of connection depends on distance. So you expect that force of connection to decrease as a function of distance. So this should probably be an e to the minus dij. So this is the model with a single species, but they look at, for instance, model with two species, chicken farms and duck farms. And these are locations again, okay? These are the number of susceptible, infectious, and recovered locations, premises doing chicken and farms in these different regions. They can compute a basic reproduction number using the type of method that I was explaining in my lecture, I mean, in the earlier part of this lecture about metapopulations. So you can compute this. You can compute a basic reproduction number for the different locations. And for instance, what can be interesting as a plot is to see how this reproduction number organizes as a function of the farm density. And you can see that usually when farm density is lower, the reproduction number is lower and increases when the farm density is higher, although you can have some farms um, in high density that have a low reproduction number. You see this is 1 here. So below this line here, you expect that the disease will not spread. But these are the individual reproduction numbers. Of course, the whole system is coupled through space. And so in terms of a propagation throughout the system, this may change. Here they're looking at culling radius. So that's an important spatial take on the problem, is that you can change the radius for which you curl if you detect an infection. So very much the same way as we saw for foot and mouth disease, we obtain the same type of. I mean, we the same is done for poultry farms. And here they look at, so the final size that they mention here is the number of farms. This is a sort of counterintuitive to what we typically think of as final size. This is final size in terms of number of unaffected farms. So the number of susceptible farms that are still susceptible at the end of the epidemic. Typically, we think of final size more as, well, I mean, no, it would be the attack rate. So final size is good. But final size for S, I should specify. So this is the ideal final size in the sense of this is where you have the most farms unaffected by the epidemic, still susceptible at the end of the epidemic. And you can see that, interestingly, this does not mean that your culling radius is very large or very small. A reasonable culling radius of about 2 point something kilometers is ideal for this. And if you think about it, that sort of makes sense in terms of spatial spread. If you curl very far, you're still going to have long distance events, um, and the part of the final size, the farms that you've removed because you've culled them, they're not part of the final size, of course. So when you increase that radius, you're destroying a lot of farms that don't necessarily need to be destroyed. And on top of that, you can have long distance events that would seed things a bit further away. Whereas this shorter range culling radius is, well, in that case, ideal. And here we're not showing it here, but this corresponds to this dip here in the number of infected premises. Um, and the last graph that I want to show is this one, which is showing the same, well, I mean, it's slightly different parameters here, but the same culling radius when you have 459 farms infected, sorry, that remain susceptible at the end of the epidemic, and that corresponds to this culling radius here. And this shows you how that number of that final size decreases as you move away from this radius of cutting. And that's it. So very briefly, what I wanted to show you through these models is not, I didn't want to get into details, and like there's about 15 papers that were discussed here, and if you want to get into more detail, I really recommend that you look at them. What I wanted to highlight is a variety of ways that have been taken to consider the control, I mean, the spread on the one hand, but also controlling that spread on the other hand of the infection based on spatial aspects. Okay, and there's a variety of ways that space comes in, as you've seen. There's a variety of ways to model space. Essentially, a lot of them revolve around metapopulation models, but what a metapopulation model looks like is a bit different for everybody, which is good. The type of metapopulation models I presented in the previous video is one way to apprehend that problem, but here you see that in fact a lot of people did not incorporate explicit movement of individuals, which, depending on the type of data you have, is probably a very good way of going about to do things. And then control measures were looked at, and a variety of control measures were looked at. Some of them involve restriction of movement, some of them involve culling, some of them involve vaccination, and there's combinations, of course, of all of those. And I think models here have a large role to play because these are, if you remember my introductory lecture on diseases of livestock, I was pointing out that these represent a livelihood of people. Even if you take away the feeding others part of the equation, people depend on this to make their living. And so when you take culling measures, you're essentially extinguishing their means of living. And so it's important to understand what your measures can do. And with models, we're able to address and play with some of those components without actually having to go through. Of course, I showed 3 times some graphs that dealt with the sort of inadequation between models and reality in terms of what you can observe, what you assume in a model, and what you can observe in reality. And this is something that you also should always bear in mind. Yes, models help, but don't overestimate their capacity, and in particular, be wary and aware of what limitations there are in terms of the variables you observe and that type of thing.